Let's start our third meeting. Uh, Today we'll discuss those topics, that is interior, closer, and subspace. So can you hear me? Hello everyone. Am I audible? Okay, good. So we already seen topology is nothing but collection of open sets. Open sets. That is, in terms of basis, we can define a topology as collection of open sets, and we define open set, that is, we can define basis, and after defining basis we can define a topology generated by that basis, and we have already seen that is actually collection of all open sets, union of those bases elements. And we also define that A is closed, so X be a topological space. A set A is closed if and only if the complement of that set is open. This is the definition of closed. For example, let us consider this topology on 3 points. Empty X, let X equal to this ABC 3 points. Consider this topology, it contains A and it contains AB. Only 3. So let us also increase AB, and suppose X is ABC. This is the topology. Then you can see that A is open in the topology because this A belongs to tau, therefore A is open. So now what about B? Is B open? You can see that B cannot be open because B does not belong to tau. Now if something is not open, then can we say that is closed? We can't. Why? Because we can see what are the complements, what are the all closed sets. In this topology, what are the closed sets? Closed sets are, so empty is there, therefore what is the complement of empty? It is the whole X. X is there, so complement of X is empty. A is there, so remove A from this set, we'll get BC. So this is closed, and remove A and B from this ABC, we'll get A. So those are actually, we get C. So those are actually closed sets. Okay. So from this example, we can see that it is possible. From this example, it is clear that complement. Something is not open. That does not mean it will be closed, and vice versa. So another question: is it possible to be open and closed simultaneously? Let us consider the discrete topology. Yes, the answer is true. Okay. Let us consider the indiscrete topology on these 2 points. Let X equal to AB and consider indiscrete topology, tau I, maybe this small I, indiscrete topology, or whatever you write. It consists those 2 things. Yes. Yes, exactly. So a door can either be open or closed. That is, it cannot be open and closed simultaneously, but in this case, it can be both open and closed. So here the definition open and closed, it is different. So phi, we can see that those are actually open sets, and closed sets are complement of empty, which is x, and complement of x, which is empty. So those are actually closed sets. Okay. Now, can we define a topology in terms of closed sets only? So it is possible, right? Because topology means collection of open sets. But if we know all those complements, then just take. So we know this fact, right? Complement of complement is A. So if those elements are given, those closed sets are given, then we can take complements and we can create the whole topology, right? For example, in this case, if those sets are given, then we can create the topology by taking complement of those sets. So from here it is clear that topology can be prescribed. Okay. Now let us see some more example. So if we consider cofinite topology, then what are the closed sets? It contains empty, yes, either empty or either x or complement of that set must be finite. U is open if complement of U is finite. Okay. In this case, those are topology. That is, so you can see empty is already there because okay. Empty and the open sets will look like those only take those sets such that complement is finite. So those are actually that is the cofinite topology. Then what will be complement of those sets? Complement of empty, take complement, then empty complement will give me the whole set X. Okay. Yes. So I am considering cofinite topology on a set X. And what will be complement of U? That is U complement. Okay. Therefore, from here, what are all closed sets? So closed sets are either X or any finite set. Okay. Now, similarly, let us consider co-countable topology. Then tau, the topology will contain empty or something such that complement of that set is countable set. Okay. Then what will be complement of empty? It is X, and complement of U it is in this case let us consider R, real number. So complement of U it will be U complement, or we can write R minus U. Okay. So the question is, are those are actually, yes, so those are actually closed sets. Now if we ask that is a finite set closed here? Yes, since finite set is countable, so it is closed. Okay. So those are a few examples, and we also note that in topology we have seen that arbitrary union of open set is open and finite intersection of closed set is closed. So similar dual kind of result is true here. So closed set in this case it will be the opposite property. So finite union of closed set is closed and arbitrary intersection intersection of closed set is closed. Okay, you can easily check this property because it is taking the complement. So something is closed means let me see why this is true. The second one. So take arbitrary intersection. So something is closed mean it will look like complement of some open set. So we are taking arbitrary intersection of this those kind of closed set. Okay, closed set will look like U alpha complement, while U alphas are open set, and it is clear that this is same as um, by using De Morgan's law. This is actually union of U alpha and take complement after. Okay, and we know those that is open because arbitrary union is open. Arbitrary union of open set is open, and again taking closure of complement of that open set, that will give me closed set. Okay. From here it is clear that arbitrary question closed sets from assignment. Okay, you may ask later. And now let us see what is a subspace topology. Okay. Uh, uh, is it from that previous one's discussion? Subspace topology is not covered in this way. Okay, though it is not covered, let me cover it because I have some questions from this subspace topology, and it is not actually hard. Let us define it. You can easily understand. Let us define what is subspace topology. It is very simple actually, subspace. So suppose let A be a subset of X. Okay, and X is equipped with a topology tau. There is a topology. So tau is a topology on X. Now can we topologize this A? The answer is yes. We can always find such kind of topology. So let us look an example. Then it will be more easier to understand. So this is R. We can treat this real line as a subspace of R2, right? So in this case, A is R and R2 is the whole X. Now, what are the basis of this R2? Those will form a basis, right? Some uh, network issue. Basis, yes, those forms a basis, right? Now if we here intersects with real number, then we can see we will get those kind of open interval. For example, intersecting this with R2, that will give me empty, but intersecting this open ball with this R, that will give me this kind of interval. And we know that is actually basis, right? Those open interval, some kind of A comma B, that forms a basis for R. So that story goes for any for more general case, not only as R, not only for R as a subspace of R. Okay, so we can define a topology on A. So define a topology like this. Let me denote it by tau A. U intersection A. So take all those X. That is saying U belongs to tau. That is U belongs to tau. So I am taking all those open set and I am taking intersection with this A. So here A is R. So I am taking intersection with this A. And we will get some kind of topological. Okay. So that is the definition of subspace. Sorry. Okay. This is the definition of subspace topology. Okay. And the important thing is that if this if script B is a basis for tau, then we can define, suppose we define this BA by taking those B and intersecting with A, where B belongs to the script B, that forms a basis for tau A. Okay. So intersecting the previous basis with this B, with this new A, that forms a basis. Let us consider an example. So consider A, this is closed 0, 1, union 2, 3. So A is a subset of real number and R is equipped with usual topology or standard topology. Standard topology. Standard topology is generated by those open balls, open interval, right? So R is equipped with this standard topology. Now the question is, can you see those? Can you tell me what are some open ball here, open set in A? That is not like this. The question is, it open, close 0, 1, open in A? It is not open in real number, right? Because 0 does not have any neighborhood which also contain in this A.
So it is open in subspace.
Yes. So that will be open in subspace topology. Why? Because
Because you can take, sir, open 0 2 and take intersection with A.
yes.
The close 0 1.
So something is open means it should be some open set from R which intersects with this A.
Yes, sir.
So take -1, 1, this open set. This is open in R, right? This is open in R. And take intersection with this A. Then this intersection will give me this close 0, 1, right?
Yes, sir.
Which is open. So something, so if we draw the picture, it will be more easy to understand. Suppose this is 0, this is our 1, and this is 2, 3. 2, 3. Now you can see that this open set, if we take this open set, that intersects with A here, right? That gives me this close 0. So it is just restriction of that previous open set. Restriction of this um, open interval, that gives me this close 0, 1. Therefore, this should be open in subspace topology. That is the whole story. So subspace topology is very easy. We just restrict all those open set in the subset. So whatever open set is there earlier, we just restrict to this A. We just take intersection with A. Now we define interior and closure of a space, of a set. So let A be a subset of X, and X is equipped with the topology tau. So we denote by this notation. Now, how can we define interior of A? Interior of A, sometimes it is denoted by this A degree or this kind of degree, whatever is easy. So interior of A, that means, let me draw a picture. So interior of this A, that will be given by all those open sets containing this A. Okay. So this is our A. Interior will be given by all those open sets containing this A. Those are open, so maybe it is better to write in dotted. So whatever open set is there, take those union and you will get the interior. It will almost cover everything for this picture. So interior means union of some U such that U is open and U also contain A. Is it understood? So I am taking union of all those open set which is containing A. So that's why it is called interior. I am taking union of those open set from this inside, those union of all those open set which contain in this A. So that's why this name is called interior. And what is closure of A? This is called interior of A, and this is called closure of A. So closure of A means it is just do the opposite kind of thing. So replace this union by intersection and take all those closed set. Okay, where F is closed and F containing A. So if we draw another picture, or maybe you can also copy. So let me draw another picture. So suppose this is some shape, then closure will be like take all those closed sets which contains this set. For example, this will be some closed set, but this does not contains this set. So I am removing. So this is some closed set. This is another closed set, and take all those possible closed sets and intersects all those things. So that will give something here, something like this. Okay, that will be closure. Maybe that is slightly. So that is the definition of interior and closure. So interior means take all those open sets which contain in that set, and closure means take all those closed set which contains A. Let us find interior and closure for an example. So suppose tau is this set empty X and it has A, B, some AB, and it also has X. X is already there, so X means ABC. So this forms a topology. You can see that arbitrary union and a finite intersection is already there. Now what about suppose A is C, this set. Now what is the interior of A? Can you figure it out?
So singleton C.
Interior of A. So question is singleton C a open set here?
No, sir.
So what are all those open set which contains A?
None. Empty, sir.
Then of all
A
those
interiors
open
are
sets
empty.
which contained in A. Contained in A.
Sir, X. Whole
So
set X.
X contained in A. So interior means something inside A.
Oh,
It,
sorry, sir. Yes, yes.
it cannot
So
be large.
there is no any set which contains A.
Yes. There is nothing. So the means only empty is the set which contained in A. Empty is the only open set, right? So this is actually empty.
So,
Now,
sir, A closure you have defined incorrectly, I think.
uh,
A should be subset of F.
Oh, sorry. Exactly. So those I am taking something bigger which contains A. Sorry.
Sir, same with sir open interior of A.
Oh, sorry. Exactly. I am writing something opposite. Thank you for the correction. Okay. So here you can see that interior of A is empty. Now if we choose B equal to this set, instead of AB, let us choose A comma B. Now can you figure it out, the interior of B?
Sir itself.
Okay.
B
So
itself.
yes, interior of B will be the set AB itself. Exactly. Yes. So you can see all those open set which contain in AB are empty. A is already there, B is also there. So empty A, B, and also AB. AB contain itself. So if we take the union, that will give me the same AB, which is B. Now we have not figured the closure of A. So let us figure it out. So before finding the closure, let us see what are all those closed sets. So let us write the collection of closed sets. So empty is there, therefore its complement will be X. X is there, complement will be empty.
Sir,
Yeah,
sir, sorry, is it true that the number of closed sets and number of open sets are equal?
yeah, exactly. That must be same. Their
Yes.
number will be same. So complement of A is BC. Complement of B means there is two things, A comma C, and complement of AB means C. So those are collection of all those closed sets. So let us see what is closure of A. Closure means intersection of all those closed sets containing A. So bigger closed sets which contains A and take intersection of all those closed sets.
Singleton Caesar.
Yes, singleton C, exactly. So C and there is another thing X, both contains C. So their intersection is singleton C. So what about for the second one, closure of B?
Sir, B, C.
Yes, closure of B.
Sorry, sir. Sorry, sir. Sorry,
The
sir.
only closed set is X, which
X.
contains A, right?
Yes, yes.
So X. So from here you can observe a property. The property is this, that if U is not U, A is open, then interior of A is same as A, right? Because from here it is clear that from here, see the fact that interior must be a subset, right? Because I am taking all those open set which contains in A. So interior must be smaller, something which already contain in this A. So whatever union you take, it it cannot exceed A. Therefore, interior is contained in A. But what about closure? For closure, I am taking bigger sets, right? Larger sets, and I am taking intersection. So if something is bigger, then whatever intersection we take, that will be also bigger. So closure. So this is a relation, important relation, which can be useful to find interior and closure. So sometimes I am not writing this equal. So whenever I am not writing, assume there is some equality. It is possible this also equal. Okay. So this same as this. I am using this notation as same subset equal. So that is not only one-sided. That is if and only if. And similarly, if A is closed, if and only if closure of A is same as A. This fact also you can observe from this notation, because suppose A is open, then you can choose A in this case. You can take union with A. So take all those open sets and also take A, because A also satisfy this criteria, right? But those open sets are proper. Those are subset of A. So among all those things, A is the largest possible thing. Therefore, the union will give me A, right? So if A is open, then their interior will be A. And similarly, if interior is A, then that, because you can also check that interior forms a open set, because you are taking union of open set, right? So union of open set is always open by definition of topology. Therefore, if interior of A is A, then since interior is open, interior this is open, therefore A is also open, because that is equality. Okay. Therefore, this holds. This is the same similar kind of check. You can check that closed if and only if closure is same as A. And there is another observation you can see. Observe that if you take closure and take complement of this thing, this closure, that is same as. So let me draw a picture. This is A, and this is X. So if you take closure and if you take the complement, then what will you get? Complement of this closure. So this is actually interior of the complement. Okay, this is same as interior of complement. So it is, so closure and complement, those may not come. Those in general, those will not commute. But if you replace closure with interior, then there is some kind of commutativity. So you cannot take this outside, but if you replace this with interior, then that will go. Is it clear?
Sir, if we take closure inside, sorry, complement inside and closure outside, then
Yes.
Sir, if we take complement inside and closure outside.
Okay, complement inside and closure outside. So replace A by A complement. Then what will you get? Interior of A complement,
Yes, sir.
which is the right hand side is interior of A, the left hand side is this, right? But if you take the complement again, then what will you get? So it is just a fact. Complement, if you take complement two times, you get the identity. That is, take complement of A twice, you get A. It is just using second rule. The same kind of thing also holds for the other way. That is, if you first take interior and take complement, that will give me taking
Yes,
complement
sir.
first. Okay. So this property also comes from that by definition. You can also observe from the definition there is some kind of relation is already there because complement of open is closed. It is just using that. Okay, that is very easy exercise. You can try. So those are few properties. Now the problem is from here it is easy to find interior and closure using this definition only. If we only use this definition, it is for this example it is easy. But in general, the set is infinite, and the topology may contains infinitely many open sets. So it can be hard to find all those infinitely many open set which contains A. Sorry, which contain in A. So it can be hard, right? If there are infinitely many open sets. So in this case, there is another characterization for interior and closure of A. Okay. So again, we are assuming A is a subset of X, and X is equipped with a topology tau. Okay, and let X belongs to X. So interior of A means take all those X such that it satisfies some property. X has a neighborhood contained in. So X belongs to interior A. This is true if and only if X has a neighborhood contained in A. So we may write in this way also. So X belongs to interior A if and only if X has a neighborhood which contained in A. Okay. So what will be the definition of closure? Similarly, X belongs to closure of
Largest
A.
closed set containing A.
Yes. Means X has a neighborhood which intersects A. Okay. Intersects means I am taking non-trivial intersection. That is, there must at least one element. And what is neighborhood meanings? X has a neighborhood means X contained in a open set. So neighborhood means open sets which contains X. Okay. Neighborhood is nothing but open set. Sorry. I am making some mistake. Every
Yes, sir. This is correct. Every neighborhood, sir.
Every neighborhood of X intersects. Otherwise, uh, that will be not the previous one. Okay, because you can also check with this one from this definition. If you assume this definition, it is more easy to prove this definition from this fact. Okay, so let us find interior and closure. Suppose A equal to this set, open 0, closed 1, and consider X is real number. Then what is interior of A and what will be the
X,
closure?
X is R.
Hmm?
X is R.
X is the real number with usual topology. If topology is not mentioned, then always assume that is usual topology.
Sir, open interval 0, 1. A interior.
Yes. So interior of A, it will be open 0, 1. Uh, can you see why 1 is not, 1 does not belongs to the interior?
Yes, sir.
Can you see that?
Yes, sir.
But because 1 has no neighborhood, so what a neighborhood of 1 will look like? It is 1 minus some epsilon. This is a basis, right? A basis which contains basis element which contains A. But is it possible this contain in A?
No, sir.
This is never possible, right? So there is no such a neighborhood which contain in A which also contain X. So one cannot be a interior point. Similarly, if we take any other element which does not belongs to 0, 1, that is also not a interior element. So what will be closure of A? Exactly, closure of A is 0, 1. So 0, 1 is the smallest closed set which contains A. And similarly, uh, open 0, 1 is the largest open set which is contained in A.
Yes, sir.
So again, using that definition, you can see that so it is already clear that A contain in closure of A. Therefore, this open 0 closed 1 that contain in A closure. So we only need to see that this 0 also belongs to this closure. So 0 does not belongs to A, but we only need to observe that 0 belongs to closure of. So can you see that? Because
What, sir?
what will be, yes. So take any neighborhood. So any open
What are you
neighborhood,
asking, sir?
yes. So can you see that 0 belongs to this closure?
Yes, sir.
Yeah. Any neighborhood minus epsilon comma epsilon, it must intersect A, whatever epsilon we choose. Because open 0 comma epsilon is already contained in the intersection which has infinitely many points. Okay, so that is some example. Let us see some non-trivial example. So let me consider B, which is 1 by n, and n belongs to natural number. Now the question is, what will be the interior of? So note that here the previous definition is not that much useful because you cannot see all those open set. Similarly, you cannot see all those closed sets because there are infinitely many open or infinitely many closed sets for real number. That's why this definition is very useful. That is not something new. That is if and only if. You can prove from one to another. So what will be?
Sir, we can argue this by, sir, that B is a countable set. And if
Yes, B
any,
is countable set.
yes, sir, if you take any open set contained in B, then this will be a contradiction because any open interval is uncountable. So it cannot contain, sir, any open set except, sir, empty set.
Exactly. So
So,
whatever point we choose, if we assume if we assume X belongs to interior of B, then there must exist some neighborhood which contain in B, right? This should hold if we assume that. But this is not possible because B is 1 by n, those kind of sets. It has infinitely many, not only infinitely many, it has uncountably many elements, many points, uncountably many points. And this is countable. B is countable. You can look at. So this is countable. So we are getting a contradiction. Therefore, there cannot be any x. Whatever real number you choose, that cannot belongs to the interior. So interior of B is empty. Now what about closure?
closure is, sir, zero, singleton zero.
Closure is 0. So closure, we know that closure, B closure that contains, sorry, B containing B closure. Right. Okay. So why 0 is the only 0 is so B closure is, sorry, this is not true because you can see that B also containing B bar, right? So your guess was right, but here you also need to take this B because closure is always something bigger.
Oh, sir, yes, sir.
Okay.
So zero is, sir, set of limit points. Singleton zero is
Exactly.
set of
That will
points.
be a limit point, but yes. So why 0 belongs to this B bar? So we only need to see that 0 belongs to B bar and nothing else can be there except those elements of B. So
Yes,
why
sir.
0 belongs to? Because what are the neighborhood of 0?
So using Archimedean property, we can.
Yes, Archimedean property you need to use. So take any basis neighborhood of 0. Okay, then any any neighborhood always contains some basis element. So instead of arbitrary open set, you can always choose those kind of basis element. Those
Yes,
are
sir.
if and only if. Okay, and it also makes the checking process easier because you cannot take arbitrary open set can be difficult. There are infinitely many open sets which you cannot easily guess. So instead of arbitrary open set, it is easier to check with basis element. So 0 belongs to this kind of, so whatever open set you choose, this minus epsilon comma epsilon, that always contain in that open set which contains 0. This is by definition of basis. Okay, let U be an open set containing 0. 0. Then there exists some epsilon for which this holds. There exists epsilon greater than 0 such that this holds. Okay, if this holds, then can you see that minus epsilon comma epsilon always intersects B? There is a non-trivial intersection. This is non-empty. Can you see?
Yes, sir.
This is due to Archimedean property, right?
Yes, sir.
There exists. This is true because of Archimedean property.
For any epsilon positive, there exists a capital N such that
Yes.
1 by n is smaller than
So 1 by there
epsilon.
exists n natural numbers such that 1 by n less than epsilon. So 1 by n belongs to that.
No, sir, no, sir.
Yes.
Okay, sir.
So there exists 1 by
I was saying that there exists capital N belongs to natural number such that 1 by n is less than epsilon for all n greater than or equal to capital N.
oh, that is different actually. That is not Archimedean. But if that holds, that will also hold, right? Because if you take n greater than n, that will be more smaller. So that is
Yes,
also
sir.
not. That will also. So from here you can see that closure 0 belongs to the closure, but if you take anything else, then you can see that cannot belongs to the closure, right? Because there exists a neighborhood. There is another easy way to see that nothing else can be there, because if you take complement of B, it will look like those kind of elements, right. uh, Not like that. So you can also directly argue that nothing else can be there. If x is not 0 or x is not an element from B, that cannot be in the closure. You can argue. You can prove there exists some open set which does not intersect with this 1 by n. Can you prove that?
Sorry, sir.
So I am saying that up to this we have only proved that B contained in B closure and 0 also belongs to this B closure.
Yes, sir.
But that is not enough. That gives this containment. We also need to see that anything other than those elements is not there.
Sir, this is because if we take any other element, then we can always find sir interval which is sir whose intersection with this set is sir empty.
Yes, exactly. So let me sketch the idea. How you can prove. So those are, suppose this is 1, this is 0, and those are half, 1/3 like this, 1/3, 1/4 like this. So if those are there, then pick any real number, which is none of these. So it will either belongs to the left side, negative integer. So for negative integer, it is easy. Choose this. Whatever integer you take, you can always pick a neighborhood, open interval. And you can see this open interval does not intersect any of this 1 by n. Similarly, if you pick something from the positive part, then it must be in some 1 by n, and that is x either belongs to those kind of 1 by n plus 1, 1 by n, or x is negative number. So there are two possibilities. For this case, you can always choose a real number. Take the distance from this x and 1 by n plus 1, and x from 1 by n. Take the lower one and choose that distance. That neighborhood actually works, right? This kind of neighborhood will work. Similarly, if you take something from the negative real number, take the distance of this x from 0. That neighborhood will also work. Is it clear how you can approach? That nothing else can be there. Okay, great. So those are few examples. Similarly, you can also, there is another interesting thing which you can prove, that if you take A as a set of rational number and X is real number, then what is the interior of A and what will be the closure of A?
The interior of A is empty
Yes,
and closure of A is R.
because you can see whatever open set you choose, that cannot be contained in rational number, because whatever open set you choose, there are infinitely many irrational number also. Therefore, there does not exist any open set for any point which containing Q. So interior of A is empty, and what will be the closure?
The set of real numbers.
Closure is R. So we only need to see that all irrational number also there. All irrational number belongs to the closure. How can you see that?
So because any interval contains some rational number,
Yes. So
countably many.
take any irrational number, then we can see that x minus epsilon, those kind of, take any neighborhood that intersects with, yes, exactly, density. That intersects with rational number. This is non-empty. So that's why x belongs to a closure. So those are some examples, some easy examples, and I I only need to define another thing, which is limit point. So limit point of A, it is defined by this way. So it is similar to the definition of closure, but here there is a restriction, that is x belongs to x is said to be a limit point of A if every neighborhood of x intersects A in some point other than A, other than x. So it means, so in this example, let us see the contrast. So in this example, we see that closure of this B, that is 1 by uh, all those elements of B, that is 1 by n, or there is another element 0. Now the question, can 1 by n be a limit point? So this is the question. So is it possible?
Sorry, sir.
So we have seen that closure of this B, it is 1 by n, and there is another additional element which is 0.
Yes, sir.
Now the question is, 1 by n also be a limit point?
No, sir.
Is it a limit point? No, this cannot be limit point. Yes, you are right. But why this is not a limit point? Can
Sir,
you
because
suggest?
there are sir intervals which only contains 1 by n type element, but there is no other element, sir.
Yes. Can you give me that interval? Can you suggest me that interval?
Sir, you can take, sir, 1 by n minus epsilon, 1 by n plus epsilon, where
No, no,
epsilon will.
exactly point. So that is 1 by n plus 1, that is 1 by n, and that is 1 by n minus 1. So you can just choose this 1 by n plus 1, right? whatever the smaller distance, this is smaller, right? If you
So both
let,
have, yes, sir.
let me draw, this is 1, this is half, this is 1/3. You already know this left hand side is always smaller,
Yes, sir. Yes, sir.
so you can choose that neighborhood 1 by something. It will be like this kind of neighborhood, and this does not intersect any other point than this 1 by n. So it intersects with b at this point, but this is not allowed because in the definition of limit point we need some other point than this x.
So we can take epsilon as, sir, 1 by n minus 1 by n plus 1.
Exactly. So here I am choosing this ball b1 by n with radius, or in general you can write like this 1 by n minus this 1 by n plus 1. So this is the distance. You need to just see that this distance I am taking. Okay. 1 by n comma 1 plus n. So you can see that that will lies in the interval between this 1 by n and 1 by n plus 1. Sorry, 1 by n plus 1 and 1 by n. So that will never intersects any other point than 1 by n. So just draw a picture and see what happens in the picture. Then you can easily argue, because in exams or whatever question is asked, you always need to give a particular interval. So you need to explicitly write this kind of interval. That's why you just argue from the picture. Okay, so those are a few things, and we also see that it is an observation that closure means it is either some points from this A, or there is another thing which are limit points. Okay, limit points of A, that is notation is A dash. This is the notation. So closure means something is belongs to the closure. That means it is either element from that set, or it will be a limit point. So let us solve few problems. So first problem is, which of the following are true? So a basis is given. The other question, is it a basis for standard topology? So those are actually open interval, but the problem is those are actually rational points. So the question, is it a basis for the standard topology?
Yes.
A is true. So why this is also a basis for a standard topology? How do we check? So can you see that if we write the basis for a standard topology by tau, by, so script B is already there. Let me denote it by. So can you see that topology generated by this script B, will it be finer or coarser? So what is the standard basis for a standard topology? What is the known basis?
Coarser, sir.
It will be coarser. What is the topology for? What is a basis for standard topology?
Sir, open intervals, sir, where
Yes,
it belongs
here
to R.
AB belongs to R. So you can see that B has more open sets, right?
Yes, sir.
Maybe let me denote it by B dash. This is the basis. This is a basis for standard topology. Then B dash has some more elements. Not only AB are rational, but AB are real. That is also allowed. Therefore, topology generated B dash that will be always finite. So tau b containing tau b dash. Tau b dash, that is standard topology, will be finite. STD means standard, I am writing. Standard top is finite. From here it is clear, right? Standard topology is finite. Now, yes. So, can you see the reverse inclusion? Why that reverse side also true? How do we check that?
Sir, 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 take any element from B, sir, script B.
Yes.
So for any element from that element, there should be, sir, some element from B dash, such that X belongs to that element
So,
and is
yes.
subset of
So we actually choose some element from this B dash,
no
tau B.
B, sir.
For B,
Yes, sir, B dash.
we choose from B dash and we see that that element
Yes, sir,
also
it
belongs
is.
to that B. Means not B, but uh, that is open in tau B. So how do we check something? So we need to check if something is open here, that is also open here. So it is enough to check in terms of basis element. We take some basis element from this B dash, we will check that is also open in B. Okay,
Yes, sir.
that is the way. So let C comma D that belongs to that be a basis element. Basis element from B dash, from the standard one. Okay, that is CBD are real number. CDR not may not be rational. It is real. Now we need to check for every x belongs to this CD. Let x belongs to CD. Now what do we need to see?
So there exists some element from B, such that X belongs to that element and is subset of CD.
Exactly. So can you give me that element? So x belongs to CD means C less than x. This will imply C less than x. So between C and x, there are lots of rational number, right? So
Yes,
take
sir.
any rational number.
But what is that?
Take.
What kind of rational?
Sorry, what is your question?
Sir, can you tell specifically a rational number between these two elements?
Again, use Archimedean property. Some C minus x minus 1 by n.
Yes, sir.
Oh no, there is slight issue because x can be irrational as well. So you cannot use that property. But explicitly you can, probably explicitly you can write irrational. So let us use that fact. You can check that fact. Okay. So take a rational q. Q1 belongs to q such that q belongs to c comma x. The similar kind of thing we'll do for another inequality. That is d also x. There is some rational number in between this x and d. So take q2 such that q2 belongs to x comma d. Then we will get the answer, right? Then x belongs to this q1 comma q2 and this containing c2. But note that q1 q2 this is element from this b, right? Therefore what is the conclusion? Tau b dash containing tau. Therefore those two topology are same. Hence this is true actually. Is it clear?
Yes, sir.
Okay. So one side is always easier to see that because B dash has less number of open sets. B dash has lots of more open set because it is allowed to take real number, any irrational also. So tau B dash will generate some bigger topology, more finite topology. But we see that that is not finite. That is the reverse inclusion also holds. How do we check that reverse inclusion? So we take any basis element. In terms of basis element, we can check. So take any basis element from this B dash. We'll prove that basis element is open in tau. Okay. So we have proved that this basis element CD from this tau B dash, this is open in tau. So this is true. Now what about the second one? Here it is closed AB. There is also another way you can.
So it is also true.
Yes. Another way is like this. You can always approximate rational number by any real number by some rational number. That fact is also known. So you can also use that fact to write AB as union of something such that both ends are rational. Okay, you can create a sequence such that that converges to A and another one converges to B by using rational. So there exists some sequence of rational number which converges to A from the left side, and similarly from the that is AN converges to A, and similarly
This is same as this density property of rational number.
yes, you can use that property. So using that also you can prove. Now what about the second one? Here this forms a topology of lower limit topology. So again, what are the basis for lower limit topology? So
Sir, intervals which are closed, sir, in left side and open in right
yes.
side.
So lower limit means there is some limit point in the lower side. So it will look like some A comma B such that AB belongs to R and A is strictly less than B. That is always we will assume. This is a standard, not standard. This is a basis for lower limit topology. We define lower limit topology by this basis. Now here it is given that the given basis is C. The same thing, but here AB are allowed to take rational number. Now which side you can, which inclusion you can prove from this fact?
So last one is contained in sir. B.
Yes, tau corresponding to C contained in tau corresponding to B. Right? B has more open sets, so more generating open sets, so it will generate something finer. So we can, from here it is immediate that topology generated by this B will be finer. Now how to prove the reverse side? Will reverse direction true or not? That is the question.
So it is true.
Okay, you are saying true. So let me see why this is true or not. So my claim, if A is irrational, then there will be some issue. Okay. So I am taking this kind of open set. Suppose A comma B. AB there are already AB. Let me write something different. So let me write some S1 comma S2 or ST, where ST are both irrational number. Irrational number. Now the question, is it open? Let this ST, this already belongs to this key to be, right? Now the question, is it open in C? That is topology generated by C. That is the question. Can you see? So take this S. S belongs to ST, right? S belongs to this ST. Can you find any neighborhood from this C? Can you find a neighborhood from this script C such that it contain in ST?
No, sir.
Okay. So the answer is no. There does not exist any neighborhood whose endpoints are rational, Q1, Q2 maybe. There does not exist any neighborhood where Q1, Q2 are rational,
Because it must be closed at S.
such that S belongs to Q1, Q2, that belongs to that containing ST. Because this Q1 must be S, but this is not possible, right? So the reverse side is not true. Therefore, tau B is not containing tau C. In other way, we can say that topology generated by C is strictly coarser. Okay, so tau C, topology generated by C, is strictly coarser than lower limit topology. Lower limit. So those two topology are not same. So topology generated by this new basis, that will not be lower limit topology. It is strictly coarser. So B is false. Is it clear?
Yes, sir.
Okay, great. Now this one. This is probably you know. So it's first one says closure behaves well with intersection. Is it true? A intersection B closure is same as A
Yes,
closure.
sir.
Hmm?
Yes, sir.
No, there is a problem. Take A is Q and B is irrational, complement of Q. What is A intersection B?
Empty set.
Empty. So what will be the closure? Empty.
Empty.
But what about closure of A? Closure of
R.
rational number? Yes. Both are R.
So this is subset of A closure intersection B closure.
Yes. So I am taking X equal to real number with the usual topology for creating counter example. So, so this equality does not hold, but this thing is true. That is, this to take closure of this intersection, that is containing A closure intersection B closure. Okay. Similarly, you can prove for the union of interior. There is similar kind of issue. Okay. Here, the problem is those may not overlap, but there will be the problem because they may overlap. So the dual result is also true. Dually, a union of interior of the union, that is not same as interior of A union interior of B. Again, similar kind of issue will arise. Actually,
What
this
conditions the equality will hold
uh,
for for a under what conditions equality will hold?
yes, one condition. mm, one, then that equality will hold. But otherwise, I don't know.
Sir, if A closure
Otherwise, it
in
is included.
A closure intersection B closure is empty, then this will hold, I think, because
Uh,
we are seeing this issue here that they are overlapping.
you are saying A closure?
A closure intersection B closure is empty.
Yes, you are assuming that is empty. In this case,
Closure, sir. A closure.
sorry, A
Written
closure.
like complement.
Okay, you are assuming that is empty.
Yes, sir.
Yes. In this case,
Then I think this inequality hold.
uh, means in this case, I don't know if it is unclear to me actually. So you may check if that is true or not. Okay, so in general, that is not true. That is, intersection may not commute with closure. But if you take union, then that will be true.
Sir, in that case, equality will hold because then A intersection B closure is also empty because A intersection B closure is subset of A closure intersection B closure. So if A closure intersection B closure is empty, then A
Yes,
intersection B closure.
that is true. Yes, that way it is true.
Yes,
That
this is trivial.
okay, nice. But so though intersection does not commute, but union actually commutes. So finite union, you can this equality will hold. So from this example, it is clear this is false. So since A is false, B is also false, because you can take all those other sets as empty sets. Okay, take A and B. Sorry, not empty. Take X, the whole X. Then the same intersection will give the similar kind of thing. Since A is false, B is also false. Now, what about C? So C is false because, uh,
Sir, you
sorry,
have
C is true.
sir B should be true, na, sir, because you have written a intersection of A alpha is subset of.
Sorry,
Sir, B is true or false?
A and B are false.
Sir, why B is false?
Here the inclusion is in the opposite direction, right? We know that. Uh,
No, no, sir, it is written correctly.
okay, okay. So this inclusion is okay. Sorry. So you can prove that this is actually true. By definition, you can prove something belongs to closure of A. That means it intersection all those. So you can easily prove X belongs to interior of A alpha. That actually closure of A alpha. That means every neighborhood, every neighborhood of X intersect intersection of A alpha. That means every neighborhood intersects all A alpha, right? For all alpha. That first one means X belongs to closure of A, and this is true for all alpha. Therefore, X belongs to, sorry, all means take intersection. So B is true. Okay, you are right. Now, what about C? You can check that C is true. Similar kind of check. You start from one direction, you prove that both directions are correct. Now, what about the last one? This is for B. This is for A. Now C is exercise for you.
D, D, sir, D need not be true.
D is not true. Why? That this is
Sir,
not true for
because
us.
sir, closure is sir, always a closed set. But union of arbitrary closed set need not be sir, closed.
Yes, this is one maybe one way to observe that fact. But can you explicitly give me an example for which this is not true? So recall that example 1 by n. Okay. So denote n as the singleton set 1 by n. Then what will be the arbitrary union of n? Not arbitrary union. Union over the natural number. This
So
is 1
union
by.
will be there.
Yes. Now, what is the closure of n?
Closure
Can
of
you give?
AN.
It is the singleton set n 1 by n, right? Because there is nothing else.
Yes,
You
sir, yes.
prove that that cannot belongs to the closure. Now, what about closure of union?
Closure of union is 0 and 1 by 2, 1 by 3
Yes,
union.
we have already proved this is the whole see. So there is extra element 0, 1 by n such that n belongs to n, right? We have already proved. So from here it is clear, right, that this is not same as union of n, right? So one side will hold, that is this will be always subset. You can prove because there will be some problem, that is we know that arbitrary union of open set is open, but arbitrary intersection of open set is not open. That kind of problem will arise. So you can prove this opposite direction for finite case, because finite intersection of open set is open using that idea, but the reverse direction will not hold because arbitrary intersection of open may not be open. So this is false, right? This is not true for arbitrary union. So C you can check. C is exercise for you. Now we need to find boundary and interior of the following sets. So what is the definition of boundary? Boundary of a set. Boundary
Boundary
is
of
given.
sets are any, sir, if you take any, sir, uh, neighborhood of the point, then it will intercept complement and the set,
Yes. It intersects complement and
the given set.
okay. Let me give. There are lots of ways to define boundary. This is also given in exercise, but let me the most easy definition. So boundary it is denoted by BD, BD of A, or sometimes it also denoted by del A. Okay, those are some notation. So you can define it as so take. So let me draw a picture. Then it will be more easy to understand why this is that. Or maybe the let us see the unit disk. Okay, so from this picture, what is the what will be the boundary? Can you say boundary of this unit disk?
Yes, sir, that circle.
Yes, unit circle is the boundary, right? Unit circle. Similarly, if that instead of this closed, if we consider this open unit disk, then what will be the boundary?
Boundary is empty. No, no
No,
boundary.
boundary is something which separates this A, means roughly the idea is like this. So boundary will be something which separates this A and A complement, though that is not the definition. We'll just define roughly. This should be the definition, right?
Yes, sir.
So there is also boundary in this case. So here again the unit circle is the boundary. Unit circle. So we'll define how we can modify this definition. So boundary means take closure of A and remove interior minus interior of A. Sometimes I may use int or A not. So both are notation for interior. So is it clear how can we define boundary? So closure will be the whole thing and remove the interior inside those points, just remove. Then you will get a unit circle. Similarly here also the same thing. So take the closure, you will get the closed unit disk and remove the interior thing. Again you get the unit circle. Is it clear the definition? Okay. If that is clear, let us find the boundary for A. So let me draw the picture. I'll just uh, draw and see what happens. So in A, the region is given by this.
Sir, hyperbola, sir.
Yes, it is
It's
this kind of
sector at 0,
hyperbola,
0.
but it is not only the hyperbola; it also contains those axes. Sorry, it will not contain those axes because 0 is not given, right? So this x square minus y square equal to 0, that is not given. So those x-axis and y-axis will be not there. Now can you say the boundary? What will be the boundary of this picture? So let us see what is this is our region A. Okay. So this is not there actually. X-axis are not there. So I am writing as dotted. So what will be the closure of A? Can you guess from the picture?
Closure of A.
Yes.
Sir, A union and those, sir,
Yes.
parabola.
So those axes will be also there. That will be also lies in the closure because every neighborhood intersects A,
Yes.
right? If you take any point from the axis, that will also intersect the region. So you can prove explicitly. You can also prove. Just just take the neighborhood according to the even any neighborhood you can prove. Any neighborhood intersects that region. Okay, whatever neighborhood you choose that intersects this region. So closure it will be given by this equation, right? Here 0 is not included, but we'll include these two axes. This
Yes.
axis and this axis will be included. So instead of less than, we just replace it by equality, right? Less equal. This is closure. Now what about interior? Interior of A?
Sir, x square minus y square minus x is.
Yes.
Sorry. That, sir, x square minus y square is less than 1.
Yes.
0.
So here interior means those boundaries should not be there, right? Because whatever neighborhood we choose, that does not contain in A. Some points are outside A, right? Some points of those neighborhood. So those point cannot be interior point. So we need to remove these two hyperbola. Okay. So the same equation xy belongs to R2. such that what is the relation? So here just replace by less. Then what will be the boundary point? Boundary of A.
A closure minus A interior.
Then what is that?
So x square minus y square is equal to 1 union
Yes.
x is minus the origin.
So it is given by either this. So this corresponds to these two lines or these two axes, right?
0, 0.
Okay. So there are also two other questions. Let me only solve the second one. So xy belongs to R2. Now x is rational. So the second one I cannot draw because there are lots of rational number. So it is like xy belongs to R2 given that x is rational. So it will look like something like this, those kind of straight line. But there will be no gap because it varies over all rational numbers. Now what about closure of this B?
Closure of B.
Yes, what will be that?
Sir, B union. Sir, I think the B, sir,
It is
itself.
actually dense. There means though it seems like discrete lines, but it
Sir,
will be
B
dense.
itself.
Something very dense. Okay. Only irrational points will be removed.
Sir,
Irrational
B itself.
B itself.
Yes, sir.
So what is the closure of rational number?
R.
So
Okay,
in this
sir. So
case,
B closure is R2.
yes, it will be whole R2. Same kind of idea you can use. How we have proved that closure of rational is R, you can prove this. So B closure is R2. Now what about interior of B? Will there be anything?
So interior of B is empty.
Yes, because the same problem. Whatever you choose, you cannot find any open ball around that. Whatever point you choose, if you choose rational, because those axes are removed, right? Those parallel lines are removed, so that those points will create problem. Interior of B is empty. Therefore, boundary of B, it is actually R2. So that is how we define boundary, because in general we cannot define like this. That is something which separates inside and outside. So we need to properly define something. That's why we define by closure minus interior. Take the whole closure and remove the interior parts. So here you can see that this R2, this does not make sense. In that is in practical way, we don't see there is some boundary, right? We cannot see there is some boundary. So that's why this kind of definition is needed to define for any topological space. Otherwise, this kind of guess you cannot easily guess that that will be R. So which of the followings are correct? Closure of open unit ball is a closed unit ball. Is it true? So the closed unit ball, this is actually, so open unit ball, it is defined by this, right?
Yes, sir. This is correct.
Okay, let us see. B a comma 1, this is define all x such that distance from, so that is in metric space. Otherwise, there is those kind of definition is only for metric space. So this is open unit ball. Similarly, closed unit ball, the definition is like this: take all x belongs to x such that distance from A is less equal to 1. So you are saying this is true, right? So let us see what is if that is true or not. So take R and consider discrete topology. So this is our example. So in this case, can you see what is the open ball B01? All those real number whose distance from 0 is strictly less than 1. What will be that?
Singleton X.
Yes, by definition, distance from anything other than x will be 1. So the only possibility is x itself. Now what about this B01? Distance from,
Both are
yes, 1 is also allowed. So distance from 0 to any other thing, it is 1 by definition of discrete topology, right? Discrete metric. So again, recall that discrete metric. What is the definition of discrete metric? Distance from x, distance between x, y is either 0 or 1. X equal to y, then 0. X not equal to y, it is 1. Okay, so what will be that? It will be whole R, right? Now what is the closure of B01? What will be the closure of this?
Singleton X.
Is it singleton X? Closure of this means take all those closed sets and closed set which contains X and take the intersection. So sorry, here it is not X, it is actually 0. Sorry. So B01 closure, that means intersection of all those closed set containing this 0, right? So what will be that?
Sir, only singletons are closed in discrete topology.
In discrete topology, everything is closed. Since everything is open,
Yes, sir.
every
Yes, sir.
sets are closed. So 0 is itself a closed set. So if you take intersection, we'll get
Singleton
0.
zero. Yes, sir.
Can you see that closure of this open ball? This may not be same as this closed ball.
Yes, sir. Because
That,
it is R.
okay. Similarly, you can say that interior of closed ball, it may not be same as this open ball. So this may not hold. Now, what about the second one? A is open, that implies A is not closed. Is it true?
It is not true.
Can you give me example which is both open and closed?
Sir, any set X.
Yes, empty set and the whole X. That is
Yes.
both open and, yes, exactly. Null set. So that is also false. So none of the above.
Sir,
None of the above. Yes. What is your question?
sir, closure of open unit ball is closed unit ball, sir.
Closure of,
Closure of open unit ball is closed unit ball. It is not true.
yes, that is not true actually. So this actually depends on the definition. Usually we define closed unit ball as this. So this is the standard definition, but so that is true almost everywhere. But for discrete metric, there is some problem. Okay.
Sir, sir, you have what is the sir counter example?
So this is the counter example, right? So closure of this unit ball, open unit ball, which is 0, which is not same as closed unit ball, right?
Yes, sir. Yes.
Is it understood? Okay. So there are lots of questions. First one says, so A is a subset of X, tau is topology on X, and tau A is the subspace topology, then which of the following are correct? So is subspace topology is subset of the given topology, so it is probably, let me write it as tau X. Otherwise, there is problem. So is tau A is a subset of tau X? Is
No,
it?
sir.
Okay. Why no? Why the answer is true?
Sir,
Once
why
again,
no? Because if any set is open in A, then the
yes,
subspace topology, then they need not be open in sir.
exactly. That is the thing. So let me give an counter example. Give a counter example. So consider A as this A and X as this AB, and consider topology on X is empty X and A. Now, what will be the subspace topology? Therefore, subspace topology
Sir, phi singleton A
phi and
singleton A.
singleton A, because intersecting with A will give me singleton A. Will you get anything else?
No.
So in this case, it is working. So let me modify the example slightly. So just remove this A. Take this indiscrete topology. Now, can you see that tau A is not a subset of tau X? This is
Yes,
not.
sir. Because singleton A is not open in tau
Yes,
X.
because singleton A does not belongs to tau X. Though singleton A belongs to tau A, it is not belonging to X. So this is not true. Now the second option says if A is open in X, then can you say this containment?
A is open in X.
Yes,
Yes, sir. Then this will be true because intersection belongs to topology, finite intersection.
exactly.
Finite intersection of open sets
Yes,
belongs
it
to
is by
topology.
definition, right?
Yes,
So
sir.
A containing X is open. This is open given. Okay. Then what are the open set in A? Open set in A. A typical open set, what will it look like?
A intersection, sir. Any open with any open set
Given
in tau
by,
X.
yes, A intersection some U, right?
Yes,
Such
sir.
that where U is open in X.
Tau
This is
X.
by definition. So take any open set from X and intersect with A. Now can you see that in this case A is also open? A is also open in X, that is already given.
Yes, sir.
So A is open in X, U is open in X, then what about their intersection?
It is also open in sir. Tau X.
Intersection of two open set in X. This is intersection of two, both are open set in X.
Tau
Therefore,
X, sir. Sir,
is
open sets in tau X.
exact open in tau X. Therefore, this is true, right? Therefore, that open set also belongs to tau A. Sorry, any open set from tau A also belongs to tau X. Every closed set in A, it is intersection of a closed set in X with A. Is it true?
No.
Why?
Closed set in X.
Let us see. So, suppose F is closed in A, right?
Yes,
Then,
sir.
then F complement is open in A by definition. By definition, this means F complement is U intersection A, where U is open in A. Okay, sorry, U is open in X. By
Tau X.
definition of subspace. Now take complement again. Then that is same as, so F is same as, so
U
again
complement union A
complement means
complement.
I am taking complement from this A. So take complement in A. Then what will you get?
U complement union A complement.
Yes, it is A minus U intersection A.
Union, sir. Yes, sir.
Okay, but this is same as A minus U, right? Removing intersection is same as equivalent to remove that U only. That is not giving any extra information. But what is the meaning of that?
Sir, U is sir.
So U complement it. U complement it is actually closed in X, right?
Yes, sir.
So is it clear that whatever closed set we take, it is some closed set in X intersection with A? So the same definition, that is, instead of open set we can define in terms of closed set also. So closed set will also obtain from any closed set from X and take intersection with A.
Yes, sir.
So this is true. What about the second one? X1 tau 1, that is a subspace of X2 tau 2. This is also subspace of this. Then the claim was X1 tau 1 is subspace of this X3 tau 3. Is it true? This is easy exercise. You can prove this is true. You can prove by yourself.
This is kind of transitive relation.
Yes, prove that. Prove that. This is true. Okay. So let me solve few more questions. So here you can see topology is given on 5 elements and we need to find tau A. So A is not actually given. So let me, you can prove, you can compute this, right? Suppose A is ABC. Then what will be tau A?
Tau is sir
Yes.
A empty set singleton A.
Yes. First one will be, oh, first one will be X intersect with A, that will be A. Empty intersect with A, empty. Then AB intersect with A, which will give me AB. Then after that, Intersection with ACD will give me the same A. Intersection with ABD will give me AB. And ABCD will give me ABC, right? But ABC is already covered. Okay, so this is tau. Okay, the last question probably. Okay. So in this case, A is a singleton set. Okay. Then we need to find limit points of A with respect to discrete topology and with respect to indiscrete topology. So can we find limit point of A?
Yes, sir.
So limit point may not belong to that A, that's given set. Though interior always belongs to that set, limit point may not belong to that set. Okay. Limit point can be obtained from complement. So what will be the answer for this question? So for discrete topology, can we find all those limit points for
Sir,
the given
single.
set A? Yes.
Sir, A itself.
So you are saying A
Sorry,
itself.
sir. Let X be a set containing more than one point. Yes, sir. Sorry, A itself.
Okay. So if we take A, you are saying A belongs to the limit point, right?
Yes, sir.
Then there should exist a neighborhood. So take a neighborhood. So then by definition there exists a neighborhood. Sorry, it means every neighborhood of A. So you, if you be a neighborhood, then you intersect with A non-trivially, right?
Yes, sir.
So the intersection contains a point other than this A. So is it true? Take U to be this open set, U as the single concept P. Then what will be U intersection A?
Singleton P.
So does this has any point other than P?
No, sir.
Does this have any other point?
So this is empty.
Yes. So here you can see that this is not true. Therefore, it does not have any point other than P. So therefore, A does not belong to A dash. Similarly, you can prove no other point belongs to A dash by the same logic. Instead of A, it will be more easier. If you take B, then just consider the neighborhood as B. Then that intersection will be empty. Okay. So generally this is, so it is false. That is, sorry, A dash is empty. Okay. You can prove. What about for indiscrete topology?
So P is limit point.
Yes, Prajna is saying this is exactly. So in this case, uh, the limit point will be the whole set minus that point. You need to remove the point. Sorry, we don't need, because uh, it is already given. It has more than one point. That is, even if you choose. So what are the neighborhood in indiscrete topology?
So all the subsets of X.
Either empty or X, right? So there will be only two choices. Either you need to choose empty, but empty is, you cannot choose empty. In that definition, the you must choose some non-trivial. That is a neighborhood which contains a point, right? So whatever point you choose, if you choose some x belongs to x, then the only neighborhood which contains x is the whole set. And if you take the whole set and if you intersect with a, what will be the intersection?
Sir, singleton P.
Singleton P.
This should be empty, sir.
Yes.
Sir, if A has two more than 1 point, then this is true. That set of limit points of A is, sir, X.
It is actually x minus p, right? Even more than 2 point, because p cannot
Yes,
be
sir,
a
yes,
given
sir.
point.
Correct.
If we choose any point, if x not equal to p belongs to x, then whatever neighborhood, the only neighborhood
Yes.
of x is actually x. And we can see, observe that x intersection with a is p, which is other than the point x, right? X intersection a contains a point other than a, other than x.
Yes, sir, correct.
Okay. Other than x. So only p will create some issue. So those are some very bad cases. Those kind of thing will not occur generally. So those analytical issues. So this is the last question probably. So you can find this question, find the answer of this question.
Sir, there are more questions you are hiding.
No, there are no questions. So find the closure and interior of, this is interesting question, you can try, of minus infinity comma 1 and 1 comma infinity. That will be an interesting question. So you can do it on your own. So up to this, is there any question? Yes, please go ahead. What is that question, Rajna?
So the doubt is from solutions for assignment 2.
Yes.
So, so in question, so the doubt is for question 5. I'm not sure if the answer is correct. So,
It is from which assignment?
assignment 2.
Okay, so what was that question actually?
It was about closed sets. So,
Yes.
so let A be the semi-open interval from -2 to 5.
Like this?
Yes, sir.
Okay.
And then they have given, consider the following statements and state which of them are false.
Yes.
So statement 1 is A is closed under upper limit topology on R.
Okay, is it closed
No, sir.
in upper limit topology? This is the question.
So there's two more statements.
Okay.
So again, is A closed under usual topology on R?
Okay.
And is A closed under lower limit topology on R?
Usual One option is upper limit, option 2 is usual, option 3 is lower limit. Uh, so, what is your thought?
So here, A is closed under upper limit topology, but not closed under usual and lower limit topology, right?
Okay, let us see. So, upper limit topology here, the open set will look like this, right?
Sir, it is open in upper limit topology
Um,
by definition.
So, from here, can you observe that this is open in upper limit topology?
um, yes, sir.
A is open in upper limit, but is it closed? This is the question, right?
Yes.
So we need to see the complement. What is the complement? It will look like minus infinity comma minus 2 union disjoint
Close, sir.
region.
-2 close.
Minus 2 is closed.
Sorry, 5. So the question is it open here or not? So can you see that minus infinity comma minus 2 that is not open? The problem will arise here because if you choose minus 2 this point, can you see that minus 2 has no neighborhood like this? Sorry, minus 2 has no neighborhood like this. Sorry. uh, yes, it has neighborhood. Then what is the problem?
Um, so I can take arbitrary union and
Yes,
so
so
A
this is
complement belong. This is um, A
this is
complement
actually
belongs
open.
to upper limit topology, right?
This is open. Yes, you are right. uh, we are considering upper limit topology, so this thing is open already. And we also observe that upper limit topology, it is actually it is finer than usual topology, right?
Yes, the
Yes.
5 to infinity is also open in the upper
How
limit.
upper it is finer than, maybe this is the notation, usual topology, and even that is strictly finer. So this is actually in real number, in usual topology this is open, so it is open, there is no issue. And in so this is also open in upper limit topology, right? If something is open in usual, that is also open in upper. And this only we need to see this, right? But this is open by definition. You just
Yes.
take arbitrary, means you just take union with some more other things. We can create something like this.
So this is open.
Mm.
So this is open, therefore you are right. Therefore A is closed.
It is
Closed with
closed and
respect to
open.
upper limit topology.
And so A complement is not open under usual topology.
Yes, exactly. You are right. A
So
complement is not open in usual topology.
and it's not open in lower limit topology either.
So yes, in lower limit topology, is it open or not? So this part will not create any issue by the same year. That is lower limit topology also is subspace of, not subspace. It is coarser than, sorry. Usual topology is coarser than lower limit topology. So in lower limit topology, that is open, there is no issue. You can also explicitly check this is open. And what about this part?
Um,
So this part will create issue, right? For this minus 2 point,
yes.
because if we choose this point, then what will be a neighborhood? In lower limit topology, a neighborhood, it will look like minus 2 plus epsilon comma something, some a, right?
Yes.
But that cannot be contained in a complement because there is a gap. between this -2 and 5.
Yes, sir.
So that -2 plus epsilon, that will create a problem. There will be lots of things which does not contain any complement.
Sir,
Yes.
open interval phi infinity is not open in lower
Not
limit.
open.
No, sir, it is open in lower limit topology.
Yes, it is both. In lower limit topology, this is open
Yes, sir.
because it is final.
Finer.
Yes, Pranja.
So
What?
here statement 1 is true, but 2 and 3 are false.
Yes, exactly. One is true. You are right. One is
And
true.
the question was, so the question in the assignment was, state which of the statements are false. So the
Okay.
answer should have been 2 and 3, right?
Yes, exactly. You are
But
right.
then for here in the answer, they have given the true statement as the answer. So
Okay, maybe that is an issue. You can mail them. Then,
yes, sir. I think
but
I
you are
marked
correct.
the answer correctly, but it got marked as wrong. So
Okay, that
can
is
that be
their mistake.
rectified?
But
Yes,
you
sir.
are
I
correct.
also got the same, sir.
Okay.
Sir, I
Then
have
it is
selected
not your
option.
mistake, so you can enjoy. Uh, is there anything else, Rajna? Sandeep?
No, sir. Only this.
Okay, great.
Sir,
Yes.
can you explain the last one again?
Explain the last one. Okay. So previously we have seen that usual topology is coarser than upper limit topology. So
Yes, sir.
this thing is open in usual topology, right? This kind of, because we know this kind of interval is always open in usual topology.
Sir,
Yes.
sir, is it true that a set is open in any topology if and only if it can be written as union of open sets?
Exactly. Union of those open intervals.
Yes, sir.
Because by definition, in that basis definition, we have alternatively seen that a topology generated by that basis means any open set can be written as union of those basis elements. So for real number, open intervals forms a basis. Therefore, any open set can be written as union of those open intervals.
So what, sir? What is the problem here?
What is the problem for?
The, sir, for the closeness of A in lower limit topology.
Okay, so in lower limit topology, we see that uh, what will be lower limit topology, the neighborhood will look like this kind of, like, right, some a comma b. Now can you see that whatever neighborhood you choose, so you can choose this kind of neighborhood -2 comma epsilon and epsilon dash. Is it belongs to that a complement? Is
No,
it
sir.
true?
No.
This cannot be possible, right?
Yes, sir. So,
It
so
will
minus
include
two,
-2.
minus two will be excluded from the interior.
Yes, exactly. So -2 cannot be.
Yes.
Okay.
Do you have more questions?
So,
Yes.
so can you go back to question 7?
Question 7. Yeah.
Yes, sir. Here I think for the second one,
Yes.
the set of limit points is actually X itself. Because
Uh,
the definition of limit point is for every open set in the topology. So if the open set contains point P, then there's some
Other
other
than P.
other point than P, right? So here X is the only one, only open set. So it does contain some other point than P, right? It should be just X.
so I am saying if x is not p, then x is limit point. There is no issue. But if you assume that p, so for p, you can see if we choose p, p belongs to x, then there is a problem, right?
But there's some other element than P, since X contains more than one point.
The
There's some
neighborhood must
dimension.
the neighborhood must contain other points of A. Here is
Yes.
only singleton P, so it cannot contain any other point if X is P.
So, okay, let me again write the definition of limit point. So, limit point means x belongs to A, that is said to be limit point. Limit point is a limit point if, what is the condition? Every neighborhood of x intersect, so take any neighborhood, so every neighborhood of x, so if you take a neighborhood u, okay, then u intersect a, it contains a point, this contains a point other than x, right? So if you choose x equal to p, if you choose x equal to p, then, and if you take the neighborhood x, there are only one choice, this is the only neighborhood, then what will be x intersection a?
Um,
Only
Eight, sir.
p, right?
Yes, sir.
So will it contains anything other than p
Mm.
in this case?
Oh,
So that is the only issue, right? Oh. That's why everything will be limit point, but p cannot be, but because that is the issue actually.
X in, sir, X intersection A should not be null set.
That is the definition for closure actually.
Oh,
But
okay. I'm sorry. Yeah,
okay.
it is.
No
Yeah.
problem. Okay, Sandeep, do you have anything to say? Okay. Do we have some more exercise? All units other for unit 1 to 3? Uh, okay, you can try. There are actually in that Mooncrest there are lots of exercise, and also I have suggested another book, some book, that book is already mentioned in slide 2. Francis Su, it is book by Francis Su. Yes, you can find this book. Just search Francis topology by. That is also a nice book. There are lots of nice questions. Okay. And there is another book. There are lots of exercise, but that will be harder because you are just starting. So you can look this book also. Okay. Okay. I'll send. So thank you. Let us stop. Thank you everyone for joining.
Thank you, sir.
Okay, Sandeep. I'm disconnecting.
सर
Yes.
सर बहुत अच्छा सर बहुत अच्छे